as we pick up with example 3, we're going to start looking at, again, how do I find algebraically the inverse of the function f of x. So the first thing I want to do with this example is I want to sketch out what f of x looks like, because there's something a little different going on with this one. So when I look at f of x here, I know I have a quadratic. It's been moved right 2 and up 3. So that's at 2, 3. And I have a parabola that goes like that, hitting at that 2, 3 point. Now the problem here that I run into is if I want to find the inverse of this function, I look at the vertical line test, I grab that, I pass it up. This function, this quadratic, as stated, does not have an inverse that's a function. So what we need to do is we need to just chop off part of this, cut off part of the function, and that's the part that we're going to use to find the inverse. So typically what we do is we take just that side right there. Everything for x is greater than or equal to 2. Now that'll be either given to you in the problem, or I'll guide you to help figure out what I need to cut it off at. So when we find the inverse, we're only going to be finding it for this piece right here of my function, because now I pass the horizontal line test. So if I go through my process, I write y equals instead of the f of x, and then I swap the x's and the y's. So x equals y minus 2 squared plus 3. Then solve for the y, start working outside in. So I'm going to deal with this plus 3 first. So it's x minus 3 is y minus 2 squared. Keep working outside in, so I take a square root of both sides. So the square root of x minus 3 equals y minus 2. And lastly, add the 2 over. So the square root of x minus 3 plus 2 outside the radical equals y. So I can write my inverse function, f inverse of x, equals the square root of x minus 3 plus 2. And if I go to graph him, I'm going to leave a little space there because I want to do domain and range still underneath. But f inverse of x is going to be right 3 up 2. So something like that, right there. And it looks like that. If I reflect that green over the line y equals x, I'll get my purple graph here. And he was 3, 2. So there's the inverse. We found the inverse of the quadratic once we cut off just the part that we needed to. Now if I look at the domain and range, this is where it gets kind of interesting. The domain of my original, I said, was from 2 to infinity because I cut it off. And the range is from 3 to infinity because that's the range. It starts at the 3 and goes up. If I look at my sketch for f inverse, I'll notice the domain here is from 3 to infinity, and the range is from 2 to infinity, which is kind of neat because the domain of the original became the range of the new. The x's that were domain became y's that were range, and the range of the original became the domain of the new one, of the inverse. The y's became the x's. That's what inverses do, is they swap x's and y's. Our last example of finding an inverse function deals with a rational function, and since we have not graphed rational functions yet, we're not going to sketch graphs or worry about the domain and range on this. I just want to work through my process of setting y equals instead of f of x, swap the x's and the y's, and then solve for y. First step is going to be deal with that minus 3. So x plus 3 equals 2 over y minus 2. From here on, it's just a matter of algebra. My approach is going to be cross-multiply that entire binomial up. So I have x plus 3 and y minus 2 equals 2. My gut reaction is to FOIL, but I don't want to FOIL because I'm trying to solve for y. That would add more y's into my problem. My best step is to divide each side by the x plus 3. Essentially, we're just swapping the place of the y minus 2 and the x plus 3. So that gives me y minus 2 equals 2 over x plus 3, and that leaves me just half a step from the end where I add the 2 over, so y equals 2 over x plus 3 plus 2. So that right there is my inverse function. F inverse of x is 2 over x plus 3 plus 2. Again, we don't know how to look at the domain and range of this function yet. We'll learn about that later on in the class. But for now, I just want you to work through that algebra and realize this important step right here, where essentially I just swap those two pieces, and then I solve for the y. So there's my process of going through and actually finding the inverse of a function using algebra. The last idea for this unit is how do we verify that two functions are inverses. This is just an exercise in algebra. To show their inverses, it's a two-step process. We have to show that the composition of f inverse going into f, so f of f inverse of x, when I do that I get x. And I also have to show the composition that when I put the original into the inverse, I also get x. Which makes sense. I'm trying to show that they undo each other, and I'm trying to show that it works both ways. They each undo each other. It doesn't just work one way. So when I set it up, I have to do two separate demonstrations here. So the first one I'm going to do is put f inverse into f. That's composition, so remember that goes in place of x. So I end up getting 1/2 times the 2x plus 4, and then minus 2. Distribute, that's x plus 2 minus 2, which is just x, which is what I wanted. I showed that when I do the composition, I get x out of it. I also have to show the composition the other way. So I'm going to take this guy, this whole thing, and plug it in for x there. So I end up getting 2 times the 1/2 x minus 2 plus 4. Distribute the 2. That's x minus 4 plus 4, which is x. Now, when you're demonstrating this, don't just write the original and then hop down and say x. I want to see the work in between, because you know what the answer should be. I want to see if we're able to use the algebra to get there. So that's just the first one with a linear function in his inverse. Second one is surprisingly similar, so I'm going to run through it rather quickly. If you notice right here, I give a restriction for the domain for my inverse, which in this case doesn't really matter because I'm just demonstrating they are inverses. That just makes it more mathematically correct whenever I talk about him being the inverse of that square root. So if I want to show two things, I'm going to show first that if I put the inverse into my original function, I get what I want. So that's going to be the square root of x squared minus 2 plus 2. Notice that the parentheses don't do anything for me there, so the negative 2 and 2 cancel out, and I get just x. And lastly, if I do the inverse composed with the original, that's going to be the square root of x plus 2 squared minus 2. The squared and the square root cancel out, so I get x plus 2 minus 2, which is just x. So I've demonstrated algebraically that they are inverses. I could start with either of them and then do that process we had done before, swapping the x's and y's and solving, and that would give me the inverse. But when I say verify, I just want to see that the compositions reduce down to x, both the compositions. So that's verifying inverses, along with these last two examples of how to find my inverse functions.